Hello everyone. Now this is lecture 11 of the chapter Electrochemistry, and in this lecture I will cover the topic standard hydrogen electrode. That is very important part, and you have seen that while solving the numerical problems, it was given in those problems that the standard electrode potential of Zn2 plus is plus 0.76 volt, or it was given that the standard reduction potential of copper, that is copper 2 plus copper electrode, is plus 0.34 volt. I have told you while solving the numerical problems that this is given, and let us continue with the problems with the given values, and in the upcoming lectures I will show you how to determine such values. Now it is time to find the standard electrode potential. So this lecture will be focused on the heading, that is determination of standard reduction or oxidation. So we will write redox potential. Why I am writing this? We know the electrode potential in oxidation terms is equal in magnitude but opposite in sign to that of the electrode potential in reduction terms. So the oxidation potential equals the reduction potential provided it is opposite in sign. So if we can determine the value of reduction potential, we can say that this is the oxidation potential just by multiplying -1 with it. So just by putting a negative sign or multiplying it with -1, if we have reduction potential, we can express the oxidation potential instantly, and if we are able to obtain the oxidation potential, we can instantly able to produce the reduction potential. So our motto is to determine the standard redox potential, either reduction or oxidation, redox potential of a single electrode. Of a single electrode, that is of a half cell. So let us consider a half cell where a metal, say M, is dipped in a solution containing its own ions Mn plus. So we have a equilibrium, say Mn plus N electron arrow M. So this reversible reaction is occurring at this single electrode, that is the half cell, and we intend to find the standard electrode potential for this half cell. Now no such instrument has been discovered yet which can determine the standard reduction potential of this single electrode. There is no such instrument that if you can connect that instrument to this electrode and you can determine the standard electrode potential for this half cell. So for this half cell, the standard reduction potential is E naught Mn plus M, and only using this half cell and any machine you cannot determine this absolute value. So this is the limitation. Absolute value of E0 of any half cell of E0 of any half cell cannot be determined. So what will you do to have the value of this, and where from we are writing in the numerical problems that E0 Zn Zn2 plus equals to plus 0.76 volt, or E0 Zn2 plus Zn equals to minus 0.76 volt. So, from where we are getting those standard electrode potential? That is our point of discussion today. Now, we have an instrument named potentiometer that I have discussed in earlier lecture, how to use it and what is the purpose of using it. With the help of potentiometer, if I have two half cells, say A and B, and if I connect this with salt bridge internally and externally with the help of this potentiometer, then what will this give? It can give the electromotive force of this cell. We have two half cell A and B, and we are connecting it internally with the help of salt bridge. If there are two different electrolytic solution, if there is a common electrolytic solution, then there is no necessity of using salt bridge. I have discussed all these things in previous lectures, and we are connecting these two electrodes externally with the help of a potentiometer. So, this potentiometer will give E cell. This will give the value of this galvanic cell constructed using the two half cells. Now, what is this E cell? This E cell is EA minus EB. If you use the oxidation potential method, that is, if you write the electrode potential in terms of oxidation potential, and this is EB minus EA. If you, or better write it as C, cathode, so it will be cathode. So, cathode anode, cathode minus anode, if you express the electrode potential in terms of reduction potential. So, we have two half cell A and C, it is acting as the anode, it is acting as the cathode, and you have connected them in the external wire using a potentiometer, and the potentiometer is giving you this value instantly, E cell. But see, if you use oxidation potential method, you will get this difference, and if you use the reduction potential, you will get this difference. And another thing, if you take the concentration of any species that are present within the either in anode or in cathode in standard state, that is, if it is aqueous solution of any ions, we will take it as 1 molar. If there is any gaseous component, we will take the pressure, we will maintain the pressure at 1 atm. So, if we keep these in standard state, then the potentiometer will give us the reading E0 cell. So, when not in standard state, we will get the reduction potential or oxidation potential, but when all the species are in standard state, potentiometer will give us the actually the EMF of the cell in standard state. So, it will be like as before, this E anode minus E cathode in oxidation. So, it will be E0A minus E0C when oxidation potential is taken, and cathode minus anode when reduction potential is taken. Let us take P and Q to be two different half cells, and we are connecting them with salt bridge internally if there are two different electrolytes, and we are connecting them externally in the external circuit, we are connecting them with the help of a potentiometer. So, it is the half cell P which will act as the anode, and it is the half cell Q which will act as the cathode, and when they are combined, it is giving us the galvanic cell, and we are maintaining the conditions of standard state here. So, here also we will get E0 cell to be E0P minus E0Q when expressed in oxidation potential, and it is E0, this is cathode minus anode, E0Q minus E0P when expressed in reduction potential. See. So, this is E0P minus E0Q and it is E0Q minus E0P. This change is occurring due to change in the mode of representation, but the main thing is that you are getting the potentiometer reading, but it is the difference of the absolute values. So, this is the standard oxidation potential of this half cell. This is the standard reduction potential of this half cell. These are the absolute values, but with the help of potentiometer you are not being able to determine the absolute value. You can only have the E0 cell, E0 cell, that is you will be able to determine only the difference between the absolute values. So, if you represent in oxidation potential, you will get the difference in the oxidation potential, that is the EMF of the cell, and if you represent it in reduction potential, you will get the difference in the reduction potential, that is the EMF of the cell, and if it is carried out in standard state entirely, you will get the standard EMF of the cell. So, the standard EMF of cell can be measured, the EMF of the cell can be measured, but this is equal to the difference in the absolute values, that is the difference in the reduction potential of the two electrodes or oxidation potential of the two electrodes. Then what is the procedure to determine this value or this value or this value or this value? If you can determine this value, that is the oxidation potential of this anode, and if you know it, you will be able to determine this value. So, this is known, this is known, so this will be known from this equation, but you see only this standard EMF value of this galvanic cell is known with the help of potentiometer, and there is no such instrument which can determine the absolute value of this electrode. Then what to do? I am repeating this with another set of example so that you will be able to understand. So, let us take a number of half cells A, B, C, D and so on. So, if we connect these two cells A and B, we will get this value from the potentiometer, and it will be EA naught minus EB naught. So, it will be in the difference form, and if we connect this B and C, we will get E naught cell equals to EB naught minus EC naught. So, whenever you construct a galvanic cell, you have to combine two half cells, and the potentiometer, the machine available that can give you the EMF, cannot actually measure the absolute values. It only measures the difference in the absolute values. So, whenever you try to measure, you will get only the difference. So, you get A minus B, you get B minus C, you get C minus D, you get A minus D, you are only getting the differences. Now, if you have the differences, then how will you be able to find the absolute values? See, if you have this, say A minus B equals to 3 and say B minus C equals to 5, will you be able to solve this problem? See, there are 3 variables and there are 2 equations only. So, the criteria to have the magnitude of variables is that the number of equations that are available must be at least equal to the number of variables. If the number of equations exceed, no problem, but if the number of variables exceed the number of equations, then you will not be able to determine the values of the variables. In that case, what is the option left? You have to arbitrarily consider the value of one among these variables. Among A, B and C, you have to consider arbitrarily any variable. So from this you cannot be able to get the values of A or B or C, but if you consider A to be say 15, this is the arbitrary value. This is not being obtained from this equation. This is not by any means absolute. I am considering it. So if A is 15, then A minus B equals to 3. So B equals to, it is 12, obviously. Then 15 minus 12 equals to 3. And what will be the value of C? So it implies C equals to 7. See, 12 minus 7 equals to 5. So if you put this value of A arbitrary, then you will be able to find the value of B and C. Otherwise, you will not be able to find the values of the variables. But are these the absolute values? No, these are not the absolute values. Then is this procedure wrong? No, this procedure is not wrong, though not being equal to the absolute values, since here the difference in the electrode potential will actually drive the electrons from anode to cathode. Absolute value is not important. Absolute tendency of releasing the electrons and absolute tendency of accepting the electrons is not important in a galvanic cell. Only the difference will drive the electrons. So this difference is important. So we have to consider arbitrarily the value of the electrode potential, standard electrode potential for any one of the half cell. There are huge number of half cells. That may be a gas electrode, that may be a amalgam electrode. You have to assign standard electrode potential with a arbitrary value. And if you consider this arbitrary value, you will be able to determine the standard electrode potential of all the single electrodes. So that is the issue. Now here at this point someone will ask that if I connect A and C, then you will get another equation, that is A minus C. So there are 3 equations and 3 variables that we can be able to solve. Now see, we can get A minus C from these two also. See, if we add these two, what we will get? This BB will cancel and we will get A minus C equal to 8. So if someone say connect these two cells, here it is A and B, here it is B and C, so connect A and C, so there will be 3 equations and 3 variables, so that will be solvable, but this thing will occur. So you are actually able to determine this equation using these 2 equations, so it is actually unsolvable problem. So only solution is that you have to assign arbitrary value for any of these half cell. That is called the reference electrode, whose standard electrode potential is assigned arbitrarily. The first reference electrode that was considered is the standard hydrogen electrode, and that is in abbreviation termed as the SHE. This is our topic today. So the first reference electrode, the first reference electrode is the standard hydrogen electrode, which is SHE. The first reference electrode is the standard hydrogen electrode, and this electrode is actually a platinum electrode coated with platinum block, and it is dipped in a solution containing H plus ions having activity 1, unit activity, and hydrogen gas is being bubbled into that electrode with in contact with the solution at 1 atm pressure, and the temperature is maintained constant at 25 degrees centigrade. This is the standard hydrogen electrode. So the SHE can be represented as platinum, it is H2 in gaseous form, pressure is maintained P equal to 1 atm, and it is in contact with the solution having H plus ions, aqua, and we have the activity to be 1. So, this is the representation, and what will be the diagram for this? We take a platinum electrode and we have a coating of platinum black on it. This is the inlet for the hydrogen gas, and the hydrogen gas comes in this chamber and bubbles here, so that pressure 1 atm is maintained and temperature is maintained 25 degrees centigrade. Here we have the concentration of H plus to be 1 molar, and this is platinum electrode, and this platinum electrode is coated with platinum black. What is the function of that? Platinum black has many number of micro tunnels which actually increases the surface area. Now, with increase in surface area, it will increase the rate of reaction for the osmotic pressure and the electrolytic solution tension. So, the reaction that will occur in this single electrode is like 2H plus 2 electron reversible H2. So, this reversible reaction will occur here. This is the osmotic pressure, and this is the, and this backward direction is the electrolytic solution tension. Now, you see, if surface area is increased, then what will happen? Then both the direction will have accelerated rates. So, the forward rate and the backward rate will be accelerated. Now, if both rates are accelerated, then say this is the forward rate which actually decreases, this is the forward rate which actually decreases with decrease in the concentration of the reactants, and this is the backward rate which actually increases with increase in the concentration of the products. So, it is R forward and it is R backward, this is decreasing, this is increasing, and it will meet at a time. At the point where it will meet and onwards, it will give RF equal to RB. It will give RF equal to RB. So, the rate forward equals to rate backward, that is the point of equilibrium. Now, this is time, so this will be time of attainment of equilibrium. Now, what will happen if both the rates increases? If both rate increases, then it will fall rapidly, it will also grow rapidly. So, then they will meet each other at earlier time compared to the previous cases. So, equilibrium will be achieved earlier, say T prime. So, T prime is less than Te. So, our aim to give this platinum black coating over platinum is to accelerate the rates of both forward and backward reaction, so that equilibrium between this hydrogen gas and this H plus ions within the solution will be achieved quickly. This is our aim. Now, see, we have taken the pressure to be 1 atm, that is standard state, and the activity, that is concentration, to be in standard state 1 molar, that refers to the standard state. So, this is standard hydrogen electrode, since the standard condition is maintained. Now, the reduction potential of this electrode, that is E SHE, that is E0 2H plus H2, that is the standard reduction potential of hydrogen electrode, is considered to be 0.0 volt, that is 0 volt. So, what will be the oxidation potential? Oxidation potential is negative of that of the reduction potential. So, that will also be 0 volt. This is the convention. I have shown you just now the logic of considering one of the reference electrode, one of the half cell among all the half cells. Only if you know the value of one half cell, then only you will be able to determine the absolute values of the electrode potentials of all the half cells. So, that electrode whose electrode potential is to be chosen, whose standard electrode potential is to be chosen arbitrarily, is termed as the reference electrode. So, we have the first reference electrode to be standard hydrogen electrode, and its reduction potential in standard state is considered to be 0 volt. Then what is the procedure to get the values of reduction potential of other half cell? What we will have to do is you have to connect that half cell to this standard hydrogen electrode. Now, for the time being, say we intend to determine the standard reduction potential of zinc electrode. This is our motto. See what is our heading? It is the determination of standard redox potential of a single electrode. So, our aim is to determine the standard reduction potential of zinc electrode. So, the procedure is we have to take a zinc electrode and we are dipping it in the solution containing its own ions Zn2 plus, and we are connecting these two solutions internally by salt bridge, which will remove the liquid junction potential. So, it is internally connected, and externally we connect it with a potentiometer as discussed earlier. We are connecting it with a potentiometer. Now, this potentiometer will give you the difference in the electrode potential of these two electrodes. Now, we have maintained the standard state condition for this electrode, and also we are considering the concentration of Zn2 plus electrode to be 1.0 molar. So, we are maintaining the entire galvanic cell in the standard state. So, what potentiometer will give us? It will give us E0 cell. It will give us the standard electromotive force of the entire galvanic cell. So, when you combine Zn2 plus electrode to the right hand side and the SHE to the left hand side, and you connect them with the potentiometer externally, then the data that is given by this machine is minus 0.76 volt. This is the result of experiment. You get it experimentally. So, you have the reference electrode, the SHE in the left hand, and in the right hand you are taking that half cell whose standard electrode potential you want to know. That is the topic. We want to know the standard electrode potential of a half cell, and that half cell is connected internally by the salt bridge and externally with the help of potentiometer. Now, if this is zinc electrode dipped in Zn2 plus solution having concentration 1.0 molar, that is in the standard state, then the potentiometer is giving reading minus 0.76 volt. Not reduction, not oxidation, this is the reading from this machine. Now, if you take the oxidation potential, you will be able to write in one form. If you take the reduction potential, you will be able to write in another form. Now, in oxidation potential, what will be the form? It will be E0 H2 2H plus minus E0 Zn2 plus. This is in the oxidation potential mode. you will be able to write the standard EMF of the cell in this form if you consider oxidation potential. But if you consider reduction potential, we have to write then cathode minus anode. So then it will be E0 Zn2 plus Zn minus E0 2H plus H2. Now if someone feels angry that you are writing here Zn2 plus and you are writing here Zn2 plus Zn, have you gone mad? No, you have to follow the lecture from the start, from lecture 1, and you have to practice that what I am writing is not madness, is by no means wrong. This is the oxidation potential. So the half cell must be represented as H2, H2H plus. This is referring the oxidation. This is referring the oxidation, and when I am referring it as reduction, it is Zn2 plus 2Zn. This is reduction. 2H plus 2H2. This is reduction. So I can express this standard EMF of this galvanic cell either in oxidation potential, then it will look like this, or in reduction potential, then it will look like this. In either case, this will have the same value, since this is the reading from the machine, and machine does not understand the way of writing. It actually gives the difference. It is my perception to write it in either oxidation form or in reduction form. Now see, it is the convention for the standard hydrogen electrode that the reduction potential is 0 volt. So what will be the oxidation potential? You see, the oxidation potential is actually related to the reduction potential by this relation, E ox equal to minus E RED. So you put the value, so it will also be 0 volt. Now if we put here the values, it will be 0 minus E0 Zn2 plus, and here it will be E0 Zn2 plus Zn minus 0 volt. 0 volt. See, this is the reduction potential of the standard hydrogen electrode, it is 0 volt, and it is the oxidation potential of the standard hydrogen electrode. This is also, this oxidation potential, this is also 0 volt. Now it is equals to minus E0 Zn2 plus. Now this value is equal to minus 0.76. You see, I am continuing this expression, or E0 Zn2 plus equals to plus 0.76 volt. This is the standard electrode potential of Zn2 plus electrode, and since this is in oxidation, this is the standard oxidation potential of zinc electrode, and the magnitude is plus 0.76 volt. Now in this method, what it will give? See, this is minus 0, so this expression will be equal to E0 Zn2 plus Zn, or E0 Zn2 plus Zn is equal to this value, minus 0.76 volt. So the standard reduction potential of zinc electrode is minus 0.76 volt, and this must be, since E oxidation is negative of E reduction. So this is the reduction potential, it is minus, it is the oxidation potential, it is plus. Now you can recall the previous problems, numerical problems, where it was given that the oxidation potential of zinc is plus 0.76 volt, or I have used these values in Daniell cell, and there I have told you that I will show you how to determine the values. So this is the way to determine the standard reduction potential or oxidation potential of any half cell. So just a revision, how will you get it? So what you want the standard electrode potential of any half cell. For this you have to connect that half cell maintaining the standard state to the standard hydrogen electrode. Keep your half cell in the right side and connect them internally with the salt bridge, connect them externally with the potentiometer. Take the reading. So, that reading will be E0 cell of this galvanic cell. Now, if you represent in oxidation potential, then you will subtract cathode from anode, and if you represent it in reduction potential, you will subtract anode from cathode. So, you see, in oxidation potential, this cathode is subtracted from this cathode, Zn is subtracted from this anode, and in reduction potential this anode is subtracted from this cathode. So, maintain the formalities, and when you put the convention, that is E0 H2 2H plus or E0 2H plus H2 equals to 0, you can get the value of this electrode potential for this half cell. So, in this way you replace this half cell by another half cell, maintain the standard state and take the reading, and you will get the standard electrode potential. So, this is the procedure. If you take copper, then it will give you E0 copper 2 plus copper equals to plus 0.34 volt, and for this one we get this minus 0.76 volt. So, this is the procedure, and if there is any query, further query, do not hesitate, feel free to contact me either in the comment section or you may contact me in email. So, stay with me, I will continue with some other reference electrodes in the next lecture, in lecture 12.